Okay, let us start. So in the last lecture, we saw this feedback linearization design of a tracking controller or a servo controller. So we had a system x dot is equal to f of x plus g of x u. This was called an affine system. And for this affine system, we would like to design a tracking controller. The output is given as a function of, in general, a nonlinear function of the state. So here what we would like is that we would like this output to follow a reference signal r of t. So we define the error signal r of t minus y of t, and we want this to go to 0 as t goes to infinity by satisfying some performance requirements. And these performance requirements are actually given by some requirements on how this e of t should go to 0. For example, what should be its time constant, what should be its oscillation frequency, etc. So we are given some performance requirements on how this e of t should converge to 0 as t goes to infinity, and we would like this output to follow this reference based on those performance requirements. So remember, in the last lecture, we saw some design steps. The first design step was to find the relative degree of this system. And it is found by taking the derivatives of y until the input appears on the right-hand side. And remember, in the most general case, we call the order of the derivative in which the input appears on the right-hand side as the relative degree of the system. This is shown as Rd, and this Rd is between 1 and n, where n is the dimension of the state vector. And when we calculate this Rd, we know that the right-hand side is going to be given as follows: alpha 0 times y, alpha 1 times y to the first order derivative, going until alpha Rd minus 1 to the y, Rd minus first order derivative. These are some linear terms in y, and we don't want to put these linear terms into the feed-forward part of the controller. That is why we separate them from the other terms. These are terms linear in y. And on the right-hand side, we could have some nonlinear terms in terms of the state variables, x1, x2, going until xn. These are nonlinear terms in the state variables, x1 going until xn. Here we can have y as well. It really doesn't matter much. Plus, I have some g1 of x1 to xn times the input u. And these are the input-related terms. And the good thing about these input-related terms are that they are linear in the input. So solving for the input u is quite easy in this equation. And this is happening because we're considering an affine system. If the system was not affine in u, in such a case, we will not have these terms linear in u, so that we will not be able to solve this equation in terms of u quite easily. So here, after this point, what we do is the following. We collect all of the linear terms in y on the left-hand side. Y to the Rd minus alpha Rd minus 1. Y to the Rd minus 1, first order derivative. These continue until alpha 0 y. And then we have only on the right-hand side, we have only the remaining terms, which are these f1 and g1u. So I have f1 of x1 to xn plus g1 of x1 to xn. Okay. So in this case, we can actually start designing the controller here. U is going to be our controller, is going to be given by our controller. What is control? Control is choosing the input of the system such that the output does something that we would like. So here, with the aim of control, we choose what this u should be. So we choose this u as follows. U is going to have three distinct terms. The first part is called feed-forward part. Okay. plus we have a feedback error control part, plus we have a feedback linearization part. Okay, that is what we have. And we could actually write these terms as follows. U is going to be, the first thing that I do is that I cancel this G1 in front of U, okay? So that is what we do first. G1 of x1, x2 going until xn here. And then next to multiplying that will be these three terms, okay? The first terms are related to the feed-forward part. Feed-forward part, what it does is that it replicates this left-hand side in terms of the reference input. Feed-forward parts will come by replicating the left-hand side in terms of the reference input. So we have reference input to the Rd order derivative minus alpha Rd minus 1, reference input Rd minus first order derivative. And these continue until alpha 0 R, okay? So what I did was I just replicated the left-hand side in terms of the reference input, okay? That is what I wrote these terms by replacing by R. So then this part is called the feed-forward part, okay? That is feed-forward parts of the input, or feed-forward parts of the controller in that case. And the next part is called the feedback error control part, and these are written in terms of the error signal, okay? We start adding terms in terms of the error, K0E, K1 E dot, and we continue adding the derivatives of the error until the derivative order 1 less than the relative degree of the system here, okay? So we continue adding the derivatives of the error until Rd minus first order, okay? Whatever Rd is. Rd is going to be between 1 and n. So this is going to be Rd minus first order. These parts are called the feedback error control parts of the controller, okay? And finally, what I need to do is that I need to cancel these nonlinear terms. I cancel these nonlinearities by this 1 over G1 division, and I need to cancel these ones as well, okay? So here, in order to be able to cancel them, I add a term into the controller, f1 of x1 to xn here, okay? And that is going to complete our controller design. So here, these terms are nothing but the feedback linearization parts. And this is our main controller equation. This is what we choose as our control based on the state and the reference and the error signals. Okay? This is called a feedback linearization based tracking or servo controller for our system. And why do we do it? We do it for Y to actually follow R of t as close as possible. And then I substitute this equation, this input, into my system. This is my open loop system. Okay? So this equation represents the open loop system. This is my control law, okay? That determines what the controller does. And when I substitute this equation into my open loop system, I get the closed loop system equation. Okay? That is what it is going to give me. So now let us try to substitute it. Y to the Rd order derivative minus alpha Rd minus 1, y to the Rd minus first order derivative. These minus signs will continue until alpha 0, y here. And let us see what is going to happen when I substitute this u into this equation. The first thing that's going to happen is that these g1s will cancel. Okay? And then on the right-hand side, what is going to, and g1s will cancel and f1s will cancel. So we are going to have this one cancelling, and this g1 is actually cancelling. So what is going to be left are these parts of the input. Okay, the other parts, this is going to cancel, this is going to cancel. So on the right-hand side, I'm going to have this feed-forward part, r to the rd minus alpha rd minus 1, r to the rd minus first order derivative, minus alpha 0 r here, plus k0e, and these are going to continue until k rd minus 1 e to the rd minus first order derivative. So now we are actually ready to convert this equation into an equation that involves only the error signal. Okay? So all of our aim here is to reach this point where this equation can be written in terms of the error signal only. Okay? And when I can write this equation in terms of the error only, I would actually see how I can make that error signal to converge to 0 as easily as possible. So here, let us take these r terms. Maybe I can here take just these y terms to the right hand side. Okay, so that is going to be 0 here, and I can take these y terms to the right hand side. So I will have r minus y to the rd order derivative minus alpha rd minus 1. It is r minus y rd minus first order derivative. And these are going to continue until minus alpha 0, r minus y here. Plus I have k0e going until k rd minus 1 e to the rd minus first order derivative. Okay? Now this is quite good because r minus y is nothing but our error signal. Okay? R minus y is our error signal. So I'm going to replace this by e, and these are going to be. So then what I can write here, I can combine these derivative orders by the error terms quite easily. So what we are going to get here is that I will have e to the rd order derivative, okay, which is this term. I handled this. And then I have e rd minus first order derivative. One of them is here and the other one is here. So I can actually write plus k of rd minus 1 minus alpha rd minus 1. Okay? This is e rd minus first order derivative. Okay? And I can actually continue this combining these error related terms until I reach k0 minus alpha 0. Okay? And this is going to be just error signal. Okay? And that is actually going to be equal to 0. So here we see something important. At the end, if I choose this input, then the error signal is going to satisfy a homogeneous differential equation, linear constant coefficient, homogeneous differential equation. Homogeneous means the right-hand side is equal to 0, input is equal to 0. Okay? So that actually means that this error signal is only going to be non-zero due to its initial error, initial conditions. If the initial error is non-zero, then this is going to it is going to behave according to those initial conditions with some characteristic polynomial roots and exponentials, etc. So here, because this equation is linear constant coefficient differential equation, I can actually write its characteristic polynomial quite easily. So the characteristic equation for that linear constant coefficient differential equation is the following: s to the rd order power plus k rd minus alpha rd minus 1 s to the rd minus first order power, and these continue until k1 minus alpha 1 s plus k0 minus alpha 0 is equal to 0. This is the characteristic equation of the error signal dynamics. And I know that the roots of this characteristic equation will give us some pole locations. And then I know that in this error signal there will be exponentials which would involve the roots of this characteristic polynomial. For example, if I have the following differential equation, E double dot plus let us say 3E dot plus 2e is equal to 0. If I have such a differential equation, what can I say about the solution of this differential equation? I will look at the characteristic polynomial s squared plus 3s plus 2 is equal to 0. And I see that in this case, this polynomial has roots at -1 and at -2. Okay? So the characteristic polynomial roots are at s equals to -1, s equals to -2. Then I know that this error signal is going to be in the following form. Some coefficient alpha times e to the minus t plus another coefficient times e to the minus 2t. Okay? So I know that if the roots of this characteristic polynomial, if they are in the open left-out plane, in that case, the error signal is going to show such a behavior. And this alpha and beta parameters are going to be determined by the initial conditions of the error signal. And these decay parameters are going to be determined by the pole locations. If I have complex poles, in general, complex poles will give, in addition to exponentials, we will have cosine and sine terms in that case. And frequency of the cosine and sine terms will be given by the imaginary part of the poles. And the real part of the poles will determine the modulating exponentials in front of them. Okay? So here, therefore, our aim is going to be to place the poles of the error dynamics at some required locations. Okay? Let us say that we would like to choose the pole locations for the error system, error signal to be at P1, P2, going until PRD minus PRD. Okay? So in this case, I know that there are RD poles for the error system because this is an RD order differential equation. Okay? So so let us say that these are the desired pole locations. We need to translate the performance requirements into some desired pole locations. For example, performance requirements might be the time constant of the decay of the error signal to 0. That might be a performance requirement. I need to translate those requirements into some required pole positions for the error signal dynamics. Okay? And if I know these desired pole locations, I can calculate it. This is my characteristic polynomial d of s. I can always calculate d bar of s, which is the desired characteristic polynomial. This is desired characteristic polynomial. Okay? And I could actually set this to be s minus p1, s minus p2, going until s minus prd. That is going to be my desired characteristic polynomial. And now I can expand this polynomial into its individual terms. And it's going to be a polynomial which is looking like this. It is s to the power rd plus I will have d of rd minus 1 times s to the rd minus 1, going until let us say that these are barred quantities, so that they are the desired polynomial coefficients. It really doesn't matter what I call this, but currently I just decided to call them d bars. S plus d0 bar. Okay? These are the desired polynomial coefficients. Okay? And then what I have to do is that I need to choose these k parameters coming from the controller. In the controller, there are some unknown parameters here, and I know these alphas from the equation that I derived from the open loop system, and but I do not know what these k parameters should be in my feedback error controller, and that is why we are going to try to choose these k parameters based on the desired polynomial. So I will try to match the characteristic polynomial of the system to the desired characteristic polynomial. Okay? So that actually means that I'm going to equate the coefficients of these two polynomials. So I will equate ki minus alpha I to these parameters, the di bar. Okay? So that is going to give me what ki should be. Ki is going to be di bar plus alpha I. I know what alpha i's are coming from the system equations, and I know what the I bar coming from the performance requirements, and I can now find what KI's are. Okay? And that would actually complete the feedback linearization-based tracking or servo controller design. And we know that this matching the desired polynomial to the actual characteristic polynomial of the system is called actually pole placement. That is something that you must have done before in other courses. So now we are actually ready to solve an example. So we have a third order system whose equations are given as follows. E to the x2u plus x3 squared, and x2 dot is equal to x1 plus x2 squared plus e to the x2u, and I have x3 dot is equal to x1 plus x2 plus x3, and I have y. The output is defined as a third state variable. The output equation is linear, but it doesn't have to be. Okay? We can have also a nonlinear relationship in the output. It really doesn't matter. So what we have to do is that I will write the statement of the question. Design a feedback linearization tracking controller. Remember, another name for this is the servo controller. Tracking controller such that the output y of t follows the reference r of t. Reference input r of t. So we are given the performance requirement here. Place the error dynamics poles such that the error E of t converges to 0 without any oscillations. So we want in some way an overdamped response or a critically damped response. If we needed oscillations, we might have sometimes we might want an underdamped system. In that case, oscillation frequency should also omega d, damped natural frequency should also be satisfied. Should also be provided. Converges to 0 without any oscillations, and with the time constant tau is equal to 0.5 seconds. So now let us try to follow these design steps. The first thing that I will do is that I will try to identify the relative degree of the system. Well, that is why I will actually start taking the derivative of the output. Y dot is equal to x3 dot. x3 dot is going to be given x1 plus x2 plus x3 by the system dynamic equations. We see that in the first order derivative, we don't observe the input on the right hand side. So the relative degree is not 1. It is going to be larger. So I continue taking derivatives. Y double dot is equal to x1 dot plus x2 dot plus x3 dot. So I will take these from the system equations. Minus e to the x2u plus x3 squared plus x2 dot is x1 plus x2 squared plus e to the x2u. Okay. And I have finally x3 dot, which is x1 plus x2 plus x. And here it is interesting because in the first equation I had the output is equal to x3. Okay. So what I could do here, or what I should do here, is that x3 is equal to y. So why not change this x3 into y? Okay. So in that case, I would get y double dot is going to be x1 dot plus x2 dot plus this x3 is equal to y. It is going to be a linear term in y. Okay. So I could actually keep it there like that. So I can actually, instead of writing this, I could actually leave it as y. So it is going to be a linear term in y, and it's going to go into the feed-forward term. Doing this is going to reduce the load of the feedback error control. Okay. So if I keep the output terms here in this equation, and if I keep them as linear terms in y, then that is going to reduce the feedback error controller's job, because this is going to go into the feed forward controller, and in that case, the system will be able to compensate this term quite easily from the reference. Okay, that is what it can do. So here, unfortunately, these input terms are actually cancelled, and I get here the following: x3 squared plus x1 plus x2 squared plus y dot. Okay. So we see that still the input is not seen on the right hand side. So that actually means that I need to differentiate once more, and in this case, the input should actually appear in this case. So here, let us take the derivative of y for the third time. So y triple dot is going to be 2x3 dot plus I have x1 dot plus 2x2 dot plus y dot. This is y dot. So now let us substitute the derivatives. 2x3, x3 dot is x1 plus x2 plus x3. So here, putting here instead of x3 as y will not really be useful for me, because this is already a nonlinear term because of the multiplication by x3 itself. Okay, so here putting another y really will not be useful for me a lot. So that is why I can leave this as x3. Or putting here, instead of x3 squared, I could have put here just y squared. It really wouldn't be useful because it's already a nonlinear term and it has to be compensated by the feedback linearization part of the system. This is going to be a nonlinear term in y. It's not going to be something like this, which is linear in y. So I have taken care of this part, plus x1 dot. It is minus e to the x2u plus x3 squared. This is x1 dot part. Plus 2x2 times x2 dot is going to be, I have x1 plus x2 squared, and I have plus e to the x2u. And I have plus y double dot. So now I need to separate these right-hand side into three distinct parts that we have seen in our theoretical design parts. So first I need to write linear terms in y. This is going to be y double dot term. Okay. This is linear in y, so I keep it here as the first term. And then I will write the nonlinear terms in x. So I have plus 2x3, x1 plus x2 plus x3. And this is an input-related term. I will leave it out, but I have taken care of this. So I have plus x3 squared. This is nonlinear in the state. And I will also take care of this, plus 2x2, x1 plus x2 squared. Okay? These are the nonlinear terms in the state. Okay? So these are going to go to feedback linearization part. And then I will write the input-related terms. Input-related terms are, I have e to the x2u term here, e to the x2u term here. I have 2x2 minus 1, x2 minus 1, times e to the x2u. These are input-related terms. So now I can give some names to these functions so as not to repeat them over and over in my derivation. So I can define this part as f1 of, this is a function of x1, x2, and x3. Okay, that is how I can define it. And here I have my g1 function, and this is going to be g1 of x2. This is a function of only x2. So I can keep track of which state variables that these terms are dependent on. Okay? And now I can write the whole right-hand side with these abbreviations. Y double dot plus f1 of x1, x2, x3 here, plus g1 of x2 times c. This is the main equation that I can get. And here I could actually see that this RD, the relative degree of this system is actually 3. Okay? So that I have, on the left-hand side, I have RD order derivative. So now I will try to follow my design steps as closely as possible. So I will collect all of the linear terms on the left. Y triple dot minus y double dot is equal to f1 of x1, x2, x3 plus g1 of x2 times u. Now I'm actually at a point where I'm ready to choose my controller input. So this is u, which controller is going to select. This is going to be, the first thing that I will do is that I will cancel this g1, 1 over g1 of x2. I'm going to cancel it. And then I will write a controller composed of three parts. The first part is going to be the feed-forward part. That is going to replicate the left-hand side in terms of the reference signal. So R triple dot minus R double dot. This is the feed-forward part of the controller. Plus, I will add feedback error control parts. So I will keep some unknown coefficients, k0 times e plus k1 times e dot. Will I add any more terms, do you think? I need to continue the derivative orders until 1 less than the relative degree here. Plus, because relative degree is 3, I need to continue with the second order derivative term. Okay? These parts of the controller are feedback error control parts. And then what I have to do is that I need to cancel all of these nonlinearities from this equation, right? Minus f1, x1, x2, x3. That is what I have to cancel. And this part is nothing but the feedback linearization part of the controller. So now I can substitute that controller equation into this equation, and I see that this G1 is going to be cancelled, and F1 is going to cancel on the right-hand side. G1 is going to be cancelled by this, F1 is going to be cancelled by this. Okay? So on the right-hand side, the only terms left will be these. So I get here y triple dot minus y double dot is equal to r triple dot minus r double dot plus k0 e plus k1 e dot plus k2 e dot. Okay? And then I will take all of the left-hand side to the right-hand side. 0 is equal to r minus r triple dot minus y triple dot. It's going to be error triple dot minus R double dot minus Y double dot. It's going to be the error double dot plus K0 E plus K1 E dot plus K2 double dot. And now I can actually collect all of these error terms together, like terms together. So I have E triple dot, there is only one of them, and E double dot, there is two, plus K2 minus 1 E double dot, plus K1 E dot, plus K0, 0, 0. So now I'm at a position where I can actually get the characteristic polynomial of this constant coefficient homogeneous linear differential equation. So it is S cubed plus K2 minus 1S squared plus K1S plus K0. Okay? That is the characteristic polynomial, and this is the characteristic equation of this differential equation. So now what I have to do is that I need to actually find the pole locations, required pole locations coming from this performance requirement. The performance requirement that is given to us is that we really we shouldn't have any oscillations in the error signal. What does this mean in terms of the pole locations? Can I have a complex pole for the pole locations? For not having any oscillations in the error signal, we shouldn't actually have any complex poles. So all three poles, the error is a third order. The error is coming from a third order differential equation. So there are three poles in that case. So all three poles should be real. Okay. And here we are said that the time constant of the error signal should be 0.5 seconds. Okay. If I have a real pole, suppose that real pole, I have real of S, imaginary of S. Let us say that the pole is here, okay? This is the pole location P1, all right? So what type of term is it going to bring to us? This is going to bring to me a term e to the P1t in the response, okay? So if I convert this into a time constant, this is a negative number now, okay? So I can actually write this as e to the minus P1t. Now minus P1 is going to, so here P1 is a negative number, okay? And minus P1 is going to be a positive number now, okay? So now this is like a decaying exponential with a minus here now. But this minus P1 is going to be a positive number. And I can actually write this as e to the minus, I have t over minus 1 over P1. Okay? So here I see what the time constant of the exponential is. The time constant of the exponential is actually going to be the reciprocal of this pole location. Okay? Time constant is the reciprocal negative of the pole location. So if I want a time constant which is 0.5 seconds, where should this pole be? It is going to be the reciprocal of. So this distance should be the reciprocal. So here, this distance of the pole from the imaginary axis should be the reciprocal of the time constant. Okay? So that is going to be, so this distance is going to be 2, meaning that my pole should be at minus 2. Okay? So, but this is only one pole. Okay? Where should the other poles be? So this should be the dominant pole. Okay? So that is my dominant pole. And I know that my dominant pole should be at minus 2. In general, if I have to make this design rigorous, what I should do is that I need to place the other two poles far away from this pole to the left of this dominant pole. So minus, for example, at minus 6, minus 7, I could actually place these pole locations. Okay? So if I would like to be sure that the time constant of the error is 0.5 seconds, what I would do is this. But in this course, I really would not care if you place. Can I do something like this? One of the poles is at minus 2, and the other ones are at minus 1. Can I do this? Would it work in that case? In that case, what would be the time constant? 1 second in that case. So in that case, I would violate performance requirements. Okay. But here in this course, I wouldn't mind if you place all of the poles, 3 poles at the same location. But in general, if you would like to be really detailed about it, you would place the poles far away from the dominant pole, at least 3 times far away from the imaginary axis than the dominant pole. Well, that is what I would do. So there are infinitely many possibilities here. I could actually place these poles to the far part of the left of plane. But here in this course, I really wouldn't mind if you place all of the 3 poles at the same location. Okay? So let us place all of the 3 poles at -2. So I'm placing all of the poles at -2, meaning that my d bar of s, the desired characteristic polynomial, is going to be s plus 2q. Okay. And this is going to be, if I write the expanded form of this polynomial, it's going to be 6s squared plus 12s plus 8. And my d of s, the actual characteristic polynomial, d of s, is given by this. So now what I can do is that I need to equate these 2 polynomials so that my error signal has a desired property. Okay. So I will equate the coefficients. So what I would do is that d of s is going to be d bar of s, and this has to be for any s, meaning that the coefficients of those 2 polynomials should be equal. So I have k2 minus 1 is equal to 6, and I have k1 is equal to 12, and I have k0 is equal to 8. Okay? So I have k2 is equal to 7, k1 is 12, k0 is equal to 8. And that actually completes our design. So now what I would do is that I would try to illustrate what happens in the system. So here is my system. So I have x1 dot is equal to e to the minus x2u plus x3 squared. I have the system differential equations here. x1 plus x2 plus x3. This is my system. Here is my system input. This is the system output, which is x3. Okay. And now what I would do is that I would. This is my open loop system. This is the plant that I'm trying to control. Okay. So now I will try to implement this controller as a block diagram. So the first thing that I will deal with is that I will take the states out here. States are x1, x2, and x3, and somehow I need to take them out from the system. I need to be able to know them. Either I should put sensors into the system, or I need to design an observer somehow. So I take the states out from the system, and then I try to implement the following. I put a multiplier here, and this multiplier is going to multiply 1 over g1 of x2 here. Okay? This is g1 of x2, and that is why this is only dependent on the signal x2. And this is going to multiply whatever signal it gets by 1 over g1 of x2. Okay? And then here, these signals would also go to a feedback linearization part. Okay? F1 of x1, x2, x3 here, and here I need summation here, and this part here is going to be the negative of f1. So I will actually put them into my feedback linearization part. And then I have to, so here, there should become the feed-forward part. And here is my reference signal. That is R of t. And from the output, I close the loop here. This becomes my error signal. Okay? So this is my error signal. And now feedback error controller comes to here. And this controller transfer function is 8 plus 12s plus I have 7s squared. Okay? That is my feedback controller. And it's a strange controller. It requires you to take derivative of the error twice. Okay? It's not even a PD control, PD squared controller, probably. Okay? So then I need my feed forward controller, and it's going to enter here. Okay? That is going to be this is actually in that equation it is s cubed minus s squared. Okay? And it's going to take the reference signal and it's going to feed some part of the input into the controller. So that is a block diagram of the overall feedback system that one can implement for tracking the reference signal by the output. Any questions? Yes?
We're essentially canceling out the effect of nonlinear.
Yes, exactly.
So if the relationship between y and states is purely nonlinear, then it turns into pure feed-forward.
If it is purely linear, in that case, I would have. So if it is purely nonlinear, I wouldn't have this term. Okay? If it is purely nonlinear, then I wouldn't have this term. So feed-forward term would be S cubed only. Okay? So if there was actually no linear terms in my equation, then this term would be missing there. Okay, but y triple dot would always remain there still, and because it was coming from the relative degree of the system. So if everything was nonlinear, then this term would be working, this would be disappearing, and I would still have these terms as well. Okay, because in that case this wouldn't be here, and this minus one wouldn't be here. In that case, this would be K2 E double dot plus K1 E dot plus. So this term is actually reducing the effect of the feedback controller a little bit. Okay, that is the linear term. If everything was nonlinear, and only these two wouldn't be here, and the others would still be here. You need still these terms, because these terms are adjusting how the error is going to decay to zero. So unfortunately, you're going to need these. But you know that sometimes you can actually skip some of these terms. For example, if you don't like this term, then you might just skip it, and in that case, this polynomial would be given like this. Okay, then you would lose the ability to place the poles anywhere you like. Okay, but if there are some desired places which you can place the roots of this polynomial still, then you're going to be fine without K2 as well. Okay, but in general, your pole locations will be constrained to some extent, and you won't be able to place poles everywhere you like. So all of these error terms would bring you some flexibility in placing the poles anywhere you like. So now in the rest of this lecture, I will try to talk about this. Really looks perfect, right? I mean, we can do everything here, but there are significant disadvantages of this type of controllers. You can do this, but of course there might be some disadvantages that you have to deal with. The first thing that I'm going to talk about is this 1 over G1 term. Okay, we're dividing by G1 here, And remember the derivation here. In G1 here was 1 over 2x2 minus 1 times e to the x2. It was something like this. That was what G1 was. Okay? So here I'm dividing by this quantity. So what is going to happen if x2 is very close to 1 over 2? If during the operation of the system, if x2 gets very close to 1 over 2, then this term is going to blow up. Okay? That actually means that your input is going to blow up in that case. So what is going to happen in a system, if nothing breaks in your system, if nothing explodes, your actuator is going to saturate in that case. You won't be able to apply this type of torque or force if a very large one is required. In that case, you will encounter saturation and you won't be able to apply this input now. Okay? And that is going to make this controller deviate from its ideal behavior. This is what happens in ideal behavior is perfect. But if x2 gets very close to 1 over 2 here, you are going to be requiring a very large input to keep the output close to the reference. And in that case, your actuators will not be able to supply that type of input. That means that you're going to get some additional nonlinear effects, like saturation effects in your system, where which would make the controller behavior deviate from the theoretical behavior. So that is one disadvantage. And the second disadvantage is the fact that in general, we measure only the input and outputs in a control system. And we don't measure the whole state. Yes, but here, this term requires you to measure all of the state variables. Okay? And that actually means two things. Either you have to put sensors in your system, or that means actually sensor cost. Sometimes it might be impossible. Some variables in an electric motor might not be observed. You have to break the motor to put sensors inside. Sometimes it might be impossible. Sometimes, and even if it's possible, it might be costly. Okay? So you don't want to place sensors for each of the state variables into your system most of the times. That is why you might want to design an observer. But nonlinear observer design is a research topic by itself. Okay? So you need to come up with a good observer which would be able to provide estimates of these quantities, but an observer will never be able to provide exact state variable estimates. So its estimates might deviate from the true states. So then this type of ideal behavior might be lost again with an observer. Okay? So that is another disadvantage of this. So here, another thing that I can actually mention here is that in the design, we assume that we know all of the coefficients of this system. We know the state equations perfectly in order to be able to make this cancellation. What happens, for example, if this term is not x3 squared, but x3 to the power 2.1? Okay? Then my cancellation will not work, and that is going to bring us some new nonlinearities into the picture. The ideal behavior will not be preserved. Another one is you have higher order derivatives here. These higher order derivatives will amplify noise in your system. If in the reference signal, if there is noise, if in the output signal measurement, if there is noise, they are going to be amplified in this controller terms. Okay? So, and actually, such a controller is not realizable. Actually, you need to place some poles, additional poles here, in order to be able to realize it using physical components. Okay, that is what you have to do, and they're going to bring approximations. So, of course, everything is looking perfect in theory now, but in practice, you're going to encounter some difficulties that you have to overcome before you need to be able to. You can actually apply this type of control. Any questions? Soru?
Output'u sürekli olarak ilerlerken bir noktada x3 yerine y yazmıştık daha kolay.
Aha, evet.
Ama
Şu, yapmasanız da gene çalışacak. Ama o zaman şurada feedback'te cancel etmeniz gereken terimler birazcık daha artacak. O da şunun içine girmesi gerekecekti o zaman. Yani o zaman feedback linearization içine bir terim daha ekleyecektiniz. Onun feedback yerine genellikle feed forward'la halledilmesi daha işinize geliyor. Çünkü o hem bunun yükünü azaltıyor hem de bunun yükünü azaltıyor. Dolayısıyla olabildiğince terimi şunun içine koymaya çalışıyoruz ki referans hızlı bir şekilde değiştiğinde onun içindeki değişimleri burada loop'un içine aktarabilsin direkt olarak feed forward terim. Dolayısıyla onları genellikle şuradan ve şuradan çıkartmak istiyoruz ki onların yükü de onların üzerine binmesin. Başka sorusu olan? Ve observer. Hı-hı. Sensör koymak fiziksel olarak oraya bir device koyacaksınız. Yani sonuçta sensör koymak o manaya geliyor. Sistemde kaç tane position variable varsa, mesela kaç tane position velocity varsa her birisine bir tane encoder ekleyeceksiniz. Pozisyonları, velocity'leri ölçeceksiniz manasına geliyor. Bu encoder'lar her zaman böyle her yere koyabileceğiniz şeyler olmayabilirler. Mesela sistemin state'leri içerisinde bir flux variable olabilir. Elektrik motorunun içinde bir flux variable. Ne yapacağım? Ben bu sefer elektrik motorunun içini açıp içine bir tane manyetometre falan mı koymaya çalışacağım? Yapamayacağım yani onu. Yani ya sensör koymak imkansız olacak bu şekilde bazı state'ler için, ya da bu sensör demek para demek manasına gelecek. Onu sistemin içine koymak istemeyeceğim. O yüzden observer tasarlamaya çalışalım. Observer ne yapacak? Observer sadece output'u ve input'u ölçecek. Bir de bu state denklemlerini bilecek observer dediğimiz şey. Yani aslında observer'ın yaptığı şey şu olacak. Şuradan şunu alacak, şuradan şunu alacak. Bu ikisini bir tane bilgisayara vereceksiniz. Bilgisayarda bir algoritma çalışacak. Size x1 hat, x2 hat, x3 hat çıkar. Hem bu denklemleri kullanacak, hem de bu input output'ları kullanacak. Ve de bilgisayarda bir diferansiyel denklem çözücüsü aslında observer dediğimiz şey. Veya işte Kalman filtre duymuşsanız bir tane Kalman filtre veya burada nonlinear sistem olduğu için işte extended Kalman filtre falan olacak. O state'lerin estimate'lerini verecek. Artık şu gerçek state'ler yerine bu estimate'leri substitute edeceksiniz. Onlarla bu işi görmeye çalışacaksınız. Artık observer'ınız ne kadar iyi çalışıyorsa o kadar bir şeyleri cancel etmeye çalışacak o. Böyle bir durumda olacaksınız. Başka sorusu olan? Ders bitti arkadaşlar. Böyle bir durumumuz var. Yani benim anlatacağım bütün konular bitti.